Dr. Thomas Delworth is a highly respected senior scientist, get this title, at the National Oceanic and Atmospheric Administration's Geophysical Fluid Dynamics Laboratory. Wow, I thought my title was long. And serves as a division leader for seasonal and decadal variable predictability, whatever that is. We're going to hear about what that is. So, with a PhD from the University of Wisconsin. His research focuses on climate variability, predictability, and change across various timescales, ranging from seasonal to multi-decadal. Dr. Delworth's work encompasses understanding the role of oceans in climate dynamics, analyzing decadal scale changes in regional hydroclimate and extremes, including drought, and investigating the predictability of the ocean atmosphere land system on seasonal to decadal scales. A driving force behind the advancement of climate science, he has played a pivotal role in leading development efforts to build a succession of cutting-edge climate models at GFDL. Why didn't I say GFDL before? Doctor, please.
Thanks very much. I'm very, very happy to be here. This is a great group. I'm so happy to speak here. And before I start, I would like to very much encourage, if anyone has a question or comment at any time, please jump in. It's much more exciting for everyone if we hear things like that. So please do. Please jump in. So I've been doing this for a long time. I grew up in the Midwest, St. Louis, Missouri. And I was just intrigued as a kid. We'd have these huge thunderstorms coming through the area, black sky in the afternoon. And as a little kid, I just loved it. I couldn't wait for that stuff. And that just gave me just a deep, deep interest in how the whole climate system works. And then I went to graduate school, and my interest turned to longer time scales. But I entered the field just with a love of nature and how things work. And when I started in the field, which was the early 1980s, no one had heard of global warming. No one. It would have been crazy. Although the science were already on top of it. So we were already, the earliest works on global warming really from 1950s and 1960s. And so it has a very long history. It's just in the last 20 years, it's exploded on the scene. But it's really important for everyone, and especially for your kids and your grandchildren. It's going to be really a huge deal. So it's really important to understand it, so we're informed about it, and we can make the right decisions, whether it's in investments or in elections, however you want to go. You want to take this as important information to take into consideration. So please jump in at any time with questions. So I come from a place called the Geophysical Fluid Dynamics Laboratory. It is a mouthful. This is the building right here. I'm sorry that the people on this end may have a little difficulty seeing, but you'll get a vision test here. So this is a photo of our building. We're just about 1 mile from here. I think it's in that direction. I got spun around coming in here. But we've been there since about 1970. We originally formed as part of the U.S. Weather Bureau in Washington, but moved up to Princeton because we do very academic-oriented research. We're dedicated to fundamental understanding of the climate system, so we wanted to be associated with a premier academic institution. So we moved to Princeton. We have a very strong association with Princeton there. So just to set the stage of where we are, because we are a federal laboratory, so I like structure. So we are actually within the Department of Commerce. And within the Department of Commerce is the National Oceanic and Atmospheric Administration, NOAA, which probably many of you have heard of. NOAA actually occupies more than half of Department of Commerce. And under NOAA, there are different divisions. There's the National Weather Service. They make the forecasts. You hear weather forecast, you hear a lot about. National Ocean Service, maybe you hear less about. And there's something called Oceanic and Atmospheric Research. It's the research arm, sort of fortifying all of NOAA. We are part of that, and under that, we are the Geophysical Fluid Dynamics Laboratory. But we have this arrow here. We have a very strong association with Princeton University. We have a cooperative institute where we have students, postdoctoral fellows, things like that on our campus as well. A number of us have had faculty appointments where we teach graduate courses at Princeton. So it's very much an academic environment, and we benefit by the tight association with Princeton University. So our goal at GFDL, I'm sorry the print is small at the bottom of the page, is long lead time research, long lead time. We can have projects that take a decade or more to complete, to improve understanding. Understanding is key. We don't just throw darts against the wall. We have to understand the physics and chemistry of the climate system to make our best possible projections of change. And so of weather, climate, and develop computer models. That's our thing at GFDL. We build computer models of the climate system to better understand the system and to project climate change into the future as robustly, as confidently as we possibly can. So computer models are us, but it's based upon fundamental understanding of the physical climate system. So what we'd like to talk about today is three things. First, what is the greenhouse effect and what role does it play in Earth's climate? I've done a lot of teaching of classes. It's so important. You can understand this in just a few minutes. I think it's very important for everyone to have some conceptual understanding of what is the greenhouse effect. We don't need a lot of mathematical equations. We can get a very intuitive feel for that. And what role it plays in Earth's climate. It's huge. We wouldn't be here without it. A second is looking at observational evidence of climate change, all the way from ice cores to satellites. I love looking at past climates. It tells us a lot about the present and a lot about the future. It's really important to look backwards before we look forwards. Really important. And then we'll talk about future climate. How do we project climate change? And what are the likely impacts of climate change? And what are the key uncertainties? There are uncertainties. The future is not completely prescribed. There are lots of uncertainties based both upon our incomplete understanding of the system and what we as humans do in terms of future emissions. So that's what I'd like to talk about today. So this is the greenhouse effect in 2 minutes. And this is the essence of it. So every body in the universe, every physical thing in the universe gives off radiation. I do, this board does, everything. And that amount of radiation, that type of radiation, depends upon your temperature. That's why infrared sensors can track people that escaped convict in southwestern Philadelphia. He was tracked by infrared radiation. So everything in the universe gives off radiation. The kind of radiation you give off, any body gives off, is determined by the temperature of that body. So we have the sun here, really hot, gives off lots of radiation, and it gives off radiation at very short wavelengths, like X-rays, things like that, short wavelengths. That radiation, that solar radiation, because it's a very short wavelengths, penetrates the Earth's atmosphere quite easily. The Earth's atmosphere is made up of a number of gases, but for all of those, shortwave radiation penetrates completely. That's why we have sunlight. The Earth then absorbs that radiation from the sun. That's why you have a warmed planet. The Earth then can't just keep accumulating energy. It has to give that energy back up to space. We want to have an equilibrium. So that energy comes back up to space. Here's the key. The Earth, fortunately, is a lot cooler than the sun. So the Earth gives off radiation at a much longer wavelength, infrared radiation, than the sun. That radiation, as it goes up through the atmosphere, is absorbed by a few key gases in the atmosphere. It's not nitrogen, not oxygen, which form the dominant components of the atmosphere. It's a few key trace gases like carbon dioxide, like methane, like water vapor. Those trace gases absorb that outgoing long radiation and send it back to Earth. That's the essence of the greenhouse effect, because that energy then going back into the planet from the atmosphere warms the surface considerably, so it leads to a strong warming of the planet by this trapping. So Earth's average temperature is very simple physics. If there were no greenhouse effect, the average temperature of the planet would be around 0 degrees Fahrenheit. Pretty cold, we wouldn't be around. With this natural greenhouse effect, the average temperature of the planet is around 57 degrees Fahrenheit. So this natural greenhouse effect, completely non-controversial, it's responsible for life on Earth. So what's happened? We have put more of these trace gases into the atmosphere, carbon dioxide, methane, water vapor as well. And so we have a much greater effect of this trapping of radiation back to the Earth's surface. This is the essence of why the planet is warming, because of these increases of these trace gases that occur. So the question is not, is there a greenhouse effect? The question is, how much does human activity alter this natural greenhouse effect? So we have this very, very powerful natural greenhouse effect, which makes the Earth 57 degrees warmer than it would be without that. We are now adding on to that, and it's warming the planet, and that's the essence. This is really the essence of the greenhouse effect. So what we have in a stable climate, when things are in balance, we have energy coming into the Earth and outgoing energy. And before the Industrial Revolution, these were pretty much in balance. What comes in goes out. We have now perturbed that with these extra greenhouse gases, so that we have an excess of incoming radiation, which is serving to increase the heat content of the planet. Most of that extra energy goes into the oceans. It's warming up the global oceans. You've seen probably on the news how hot the Atlantic Ocean, the Pacific Ocean were this past summer. This is why. That's where most of the heat goes into the world ocean, and it's a big problem. And one of the issues that arises is the ocean takes a long time to absorb all that heat. So it's actually serving as a bit of a buffer for us by very slowly heating. But the flip side of that coin is it would take a long time to cool down too. So you build in a lot of inertia into the whole climate system through the roll of the ocean. So over 90% of the heat going to the ocean, and that contributes to sea level rise as well because of the expansion of water as it warms up. So how do we know that humans have contributed to this greenhouse effect? How do we know that? So we have measurements of carbon dioxide content in the atmosphere. These are taken every year since late 1950s. This is the Mauna Loa Observatory here on the big island of Hawaii. And they've been doing these measurements every year. So this is CO2, this red curve here. The y-axis is how much CO2 is in the atmosphere. These are in units of parts per million. 280 parts per million was the value before Industrial Revolution. When they started taking these measurements, it was like 315 in the late 1950s. We're now well over 400 parts per million. So we've increased the CO2 content of the atmosphere by almost 50% in the last 60 or 70 years. 50%, that's a big deal. It's quite actually a side note, very interesting. If you are up close, you can see these red lines go up, down every year. That's actually pointing to an important process in the climate system. The whole terrestrial ecosystem, plants, leaves, agriculture, in the summer, they all sprout, they grow. And as they grow, they take CO2 out of the atmosphere. That's their food. And that's why CO2 values are lower in the summer, because CO2 goes from the atmosphere into the plants. In fall, right about now, plants are starting to die, leaves are falling. They release that CO2 to the atmosphere as they decay. So every winter, CO2 is higher. Every summer, it's lower. This is kind of a small effect on these time scales, but on longer time scales, that can play a big role in the climate system, how the whole ecosystem changes in response to and influences CO2 in the atmosphere. So another important trace gas I forgot here, this is methane, measured at the same place. Methane is another powerful greenhouse gas. So again, it's going up, and it's going up a lot, and it's due to human activity. So what has this done to the temperature record? These are temperatures. This is something like 1960 to the present. So this is a temperature on the y-axis. And you can see these are individual yearly measurements. And you can see it's going up. It's going up by a fair amount over this time. But you can ask, hey, well, you know what? We only have measurements for this brief period of time. Couldn't this be part of some cycle? That's a very natural question. It goes up, it goes down, it goes up, it goes down. Is this part of a cycle? So tough question to ask because we've only had thermometers in wide-scale use around the planet for 130, 140 years. We can reconstruct temperatures from 100, 500, 1,000 years ago through indirect methods, which I'll describe in a minute, and they provide us perspectives on how temperature has changed over hundreds, thousands, even millions of years. So this is a reconstruction for the Northern Hemisphere from the year 1000 till the present of how temperature has changed. This solid black line is the best estimate. These shaded areas represent, there's uncertainty in these reconstructions, but this black line is pretty steady going down slightly, and then what happens here? We start putting CO2 in the atmosphere, and the temperature is just spiking like crazy. It's even higher. This was a reconstruction just the year 2000, so it's probably up here by now. So from this perspective, it certainly does not look anything like a natural cycle. We've had a pretty steady, even slowly declining temperature, which we understand, and then boom, like a rocket ship is going up. So it does not look at all like part of any sort of natural cycle. So we have other perspectives on ancient climates that, again, are very important to look at because they provide our perspective on our future climate. And it's pretty cool, the number of techniques that are used to estimate past climate. So one of the most common are people taking ice cores out of, say, the Greenland ice sheet or Antarctic. You've probably maybe every once in a while see a news story about, some new ice core is taken if you look in the news. And it's really, really interesting how this works. This is a picture. This is actually an ice core taken out from, it's probably Antarctica, maybe. And I don't know, this is probably about 3 meters long. And they take these out of the ice sheet, and they bring them inside to a laboratory right there, and they slice them. Because each year, as snow falls over Antarctica, it accumulates on the surface. Every year it does that, and it compresses, and forming ice that are deeper and deeper. Each year, as that snow falls and forms a new layer in this ice core, it traps the air that was around that year. So the little bubbles of air trapped in those ice cores. So by poor graduate students spending time in these cold laboratories, slicing these ice cores and then extracting bubbles of air and measuring the CO2 and measuring the methane in those bubbles, they can directly measure what the atmosphere was like in 1300, in the year 800. And so you form these long records of how climate has changed. We can also measure a lot of different things. There are different so-called isotopes of water, different formulations of water that can be measured and used to infer past temperatures. So these sorts of records, and many other records, are so powerful because they tell us how climate has varied over 1,000, 10,000, a million years and more. And that's really the important perspective to which we should look at with our current climate change. So with these sorts of records, and you can also, this is a ship drilling a sediment from the deep sea bottom, which there are other ways of inferring past climates from these sediment cores. So lots of interesting ways to infer past climate. When we do that, we can get records. In this case, this is atmospheric CO2. This is for the past 20,000 years. So the y-axis is how much CO2 is in the atmosphere. So it's really interesting. About 20,000 years ago, it was a little bit lower than it was, in the year 1900. That's because we were coming out of the last ice age. 20,000 years ago, we had a big ice sheet a mile thick above us, and CO2 is actually naturally lower during ice age cycles for reasons we understand. And then it was pretty steady for a long time, then look what happened. Boom, like a rocket. Again, this is an important perspective because this is not a natural cycle. This change in CO2 concentration we're seeing in the last 100 years, utterly unprecedented in anything in Earth's geologic history, anything. We can go back 100 million years. It's unprecedented. This is atmospheric methane, and again, boom, it's going up like a rocket ship. Kind of an interesting point here, this slight rise here. It may be that early human agriculture, 5,000, 8,000 years ago, in creating big rice paddies, actually tended to create more methane. So actually the earliest human influence on climate may actually predate the Industrial Revolution. It may be coincident with the agricultural revolution with rice. So it's quite an interesting story. But bottom line is, all of these changes are completely unprecedented. They are not a natural cycle. They are due to human activity, and they're much more rapid than anything we've seen in Earth's history. So let's look at then what we can reconstruct for temperature over the last, say, 10,000 years or so. This is 10,000 years before present, 8,000, 6,000, 4,000, 2,000. And this is temperature on the y-axis, departures from mean over the period 1961 to 1990. So we actually were warmer at some point here, then we had a very slow cooling, and now we're just going up like crazy. The warming is probably up here by now. We actually can understand the reasons for these slow variations. This warm period here was actually due to subtle changes in the Earth's orbit around the sun. And actually, the Earth's axis is tilted with respect to the orbit, about 23 degrees. That's why we have tropics. And the angle of that tilt of the axis varies ever so slightly every 20,000 years. But that actually influences the climate. And it's kind of humbling because these small changes in energy to the climate system result in really big changes, which is a very important way to calibrate the kind of changes we're putting in now to the system versus what we'll see in the future. So again, the warmest it's been in a long time, and the most rapid rate of warming in forever. Okay. Again, any questions, comments, please? So, yes, please. Thank you.
I know you like to be interrupted. Should we tell our children to no longer have children? Or can we wait another generation?
No. That's your choice. But what I would say, and this jumps to sort of the end, is, I mean, we need energy. We need energy. Energy is great. We want energy to cool our house, to do lots of things. It's just how we make the energy that matters. We can have lots of energy to everything we want, but if we create energy without putting fossil fuels without putting CO2 in the atmosphere, this can be changed. So the future is not written, it's what we do. There are lots of ways of generating energy now that are becoming very cost effective and don't put CO2 in the atmosphere. There are other ways, whether or not you like nuclear power generates electricity, it does not put CO2 in the atmosphere. So I'd say it really depends upon what we do collectively in that area. But energy is good. It's just how we make the energy. That's the issue. Because I don't believe in people saying, well, we have to give up something to fight this problem. I think that's a bad attitude. I want a win-win solution. A win where we have lots of energy we want to do things, but we produce it in ways that doesn't interfere with the climate system. So that's yes, please.
Actually, what is the big problem with nuclear energy that people want to cut back on that? Why don't they use more nuclear energy?
Well, I'm not an expert on that topic. I will say personally, I have no problems with nuclear energy. There are issues with it, with the fuel that's spent and how you store and process that and the threat that represents. But personally, I think the safety record of the nuclear industry is quite good. And I think that's, to me, personally, speaking not as a government person here, but as an individual, I think that should be a very important part of our future energy mix, in my opinion. Yes, please.
There's, to piggyback off of the first comment, at least somewhat, sounds like there's you somewhat paint a somewhat gloomy picture. What I wanted to ask, is there a silver lining, to borrow a meteorological metaphor? Is there a silver lining? Are some of the efforts, solar panels, recycling, or are some of our efforts at least playing out, or is that starting to become evident in the data?
I'm just going to jump ahead to something because it's really relevant to this point. Because if we continue on a trajectory of really high fossil fuel use, yeah, it is a pretty gloomy future, because we do potentially have huge amounts of warming and lots of other issues. This chart, sorry about this in the back, shows different futures scenarios. When we want to try and say what's the climate going to be like in 2060 or 2070, we have to know how much CO2 or methane we're going to put in the atmosphere between now and 2060, and that has not been determined. So we do projections of future climate under different sort of what they call scenarios, some sort of estimate of future activity. And economists and sociologists and all these people get together and come up with these scenarios based upon different assumptions. But they're really just very, they're estimates. So this is the amount of billions of tons of CO2 we put in the atmosphere per year, billions of tons. Right now we're around 40, that number is 40. And so this is going forward. This is 2015, 2050, and this is the year 2100. And so these are 5 different future scenarios of what we're going to do. This one is really almost unrealistic. It requires burning so much fossil fuel. These are more intermediate future scenarios, and these are 2 rather optimistic scenarios. Now, these 2 scenarios say that emissions of CO2 would already be declining and are going to continue to decline rapidly. That is not happening. We're seeing in the U.S. emissions declining, but worldwide we're not. We can't see that. Every country's in a different position. So to avoid those really bad outcomes, we would need to be on one of these trajectories where we're at least stabilizing and then reducing the amount of CO2 emissions. So again, this is a choice. This is not preordained. It's up to us what's going to happen. So silver lining, it's what we make of it. We can choose a silver lining or not. Our role is really looking at the physics of the climate system and saying what's going to happen. But so there are different outcomes here. All that. Okay. Thanks. Good questions. Thank you.
So sort of piggybacking that as well, somehow or another this topic seems to be politicized. How can you take what you're offering, where even I can understand it, and make it so the general public can have access to this type of information, where it's not, saying this is going to take away from something that you currently have, is going to affect your farm or whatever, your city or whatever it is. How can we take something like this, where I would imagine everyone in this room is feeling, yeah, that I can appreciate the way this is presented, and I understand it a little bit better now, and this doesn't seem like it's made up. I never felt that way anyway. But how do we share that with the general public to make sure this doesn't become a political conversation?
Gee. Yes. That's a really difficult question. I mean, people have so many different motivations and so many things. And, I will say that, like, at our institute where we are, we really try and focus on the science, being honest brokers of the science. If I make any sort of policy statements, they're my own personal opinions. And so we're on very thin ice in terms of I don't want to, say I'm advocating something in that, but I try to present the science as fairly as I could. But it is a huge problem. I think there has been a sea change, though, in the last 20 years. I've been giving talks to public for a long time, and certainly 20 years ago in an audience of this room, I would be stunned if I didn't have 6 or 10 really hardcore skeptics coming at me. But I haven't heard anyone yet, but if you are, please, that's always fun. So I think there has been a big sea change in the perception of this topic in the U.S., certainly abroad, for sure. How that translates is unclear, but I think there are reasons for optimism. The economics of renewable energy is fantastic. I mean, it's really gone way down, so that's great. Can't do it alone in wind and solar, but that's why I'm personally kind of a fan of nuclear, because it's on demand, it's 24/7 available, and that's a great way to complement the intermittency of wind power and solar power. I think you can do those things. So that's really important. Yes, please.
Yeah, I mean, the only thing, say a lot of things about nuclear power. One thing I could say is Fukushima.
How many people died?
We don't know yet.
Okay, but
We're
we
still releasing radiation into the
I do know. I don't have the numbers, but
I'm just saying that's one, and then 3 Mile Island. I mean, it's not without.
I agree with you. It's not without dangers, but everything is a risk. We took a risk driving here today, So, and we do know, for example, in coal, powered plants, we know the particulates they put out, and I don't know the numbers, but I think the number of deaths worldwide are in the tens of thousands every year because of that. So in the risk-reward trade-off, nuclear has risks, absolutely. But stepping aside. Yeah, it's really debatable, but it's a really good topic. Yes.
This gentleman here has been so patient.
Oh, I'm sorry.
I was in a flight in 2016, and there was 7-country meet
Yeah.
to decide on generating energy using the concept of hydrogen bomb, but the output would be water. You don't need uranium. Hydrogen bomb, the concept of that to create energy. There are 7 countries in the world who had met in Zurich to discuss that. And that will be the next step. I mean, you don't need uranium, because again, uranium, which country has it, which country doesn't have it. Look at it in today's geopolitical scenario. One country has it, one country doesn't have it. Whereas hydrogen bomb, if the technology is there, everybody will have it.
Yeah.
And there are 7 countries who have. 7 countries where the US, I know the person who was sitting next to me was from India. US, UK, India, and I think Germany, they're all coming together to generate this kind of technology.
Well, I mean, if there's a technology like that, I'm all for it. I'm just not aware of that, but that would be a big development. Excellent. Fusion, yeah, fusion's been 40 years away for 40 years, so. I mean, really, we have okay.
Right here.
Yeah, right.
Prince, yeah, please.
What can we do, leaving here today and into the next 12 months, 24 months, just in our own individual lives to, help improve the footprint while government and people like you decide and advise us on, how to make it better?
Well, there are different things in one's personal life. There are energy consumption that you do, and I would never advocate cutting back your convenience or cutting back. I don't believe in that, but I believe in efficiencies. So adopting technologies that you get the same stuff for less energy. I drive a hybrid car. I think that's a good choice. It's just as good as a regular car, and it's actually cheaper in the long run, and it gets twice the mileage. So I think that's a good choice. We've had other great things like LED bulbs. Wow. What a tremendous technology. Reduces energy consumption by over 80%. It's cheaper in the long run. It produces exactly the same light. So things like this in our own personal lives, I think we can we can do. But it's hard. You can do that. I mean, if everyone in the world did that, it would be great. But it's kind of hard to do a large-scale global change by, personal initiatives like that. Those are really good. But I think to make a significant change requires societal-level decisions that push us in the direction of ways of producing energy that don't emit carbon dioxide. So, and that's as far as I'll go down that line. Yes, please.
Could you speak a little bit more about the causes of the increase in methane gas as well? I know we talked a lot about CO2, but is there anything sort of
Sure.
in that category that we could be examining?
Sure. Well, I think efficiency, certainly in the energy production industry, like when they drill for natural gas, I think that like some of the methane just burn off as a waste product, or in the old Soviet Union, they had very inefficient piping systems where methane was just leaking like crazy. So I think a lot of efficiencies that can be done there. Yeah. So methane is a little harder to, and actually one of the interesting differences is that CO2, when you emit that in the atmosphere, that stays around for hundreds of years. Methane does not. Methane doesn't last as long. It's something like 10 or 20 years. So in some sense, cleaning up or reducing methane will have a much more rapid impact on global warming than CO2, because CO2 just stays around forever. So that's a rapid way. Yes, please.
So with the tree canopy getting lost because of the agriculture taking up the canopy, I mean, wouldn't we increase the canopy again, reduce CO2 just by the sheer fact they need it?
Certainly, it's a good point. So if you replant lots and lots of trees, it will be beneficial. One, as they grow, they draw down CO2 from the atmosphere, so that's a very positive thing. Also, they can provide some local cooling to environments like urban environments. Those are both positive things. The fact that trees draw CO2 out of the atmosphere, though, is a bit of a temporary effect, temporary on a time scale of 100 years. Because if you plant a whole bunch of new trees and they grow over the next 50 or 60 years, they draw down CO2, and that's great, but they store them there. But then when they die, they release them. So it's a kind of a buffer for the system. If you plant a lot of trees now, they'll draw down CO2 now for the next few decades, but then after that, they'll die and give up that CO2. So, but it's a great buffering effect. It's kind of a stabilizer in the short term that could be very, very useful. Yeah. Okay. Thanks so much. Those were all great. Yes. Someone? No. Okay. All right. Yeah. Maybe I better. So where was I? So I was going to tell you, this is what we do for a living over where we are. We make computer models of the climate system to try and make the best possible projections. If we make assumptions about the future and how much CO2 will be released, we then use these models to project, okay, what will that do to our climate? What will the impact? So the way we do this is we have some mathematical equations that represent the atmosphere and the flow, and chemical equations as well. So it's like a conservation of mass, conservation of energy, but written in more fancy terms. So like these are some equations down here that describe why the wind blows, those equations. So we have these mathematical equations. We break up the Earth's atmosphere and ocean into a whole series of boxes, lots and lots of boxes. And within each of these boxes, we write computer code that solves or provides estimates of the solution to these equations. And we use that to then project in time how the atmosphere will change, how the ocean will change, and therefore how the climate system will change. We need really, really, really big computers because there are a whole lot of these boxes. And the faster the computer you have, the smaller you can make those boxes because there are more of them, and the better your model is. Because if you make these boxes really, really small, you get a really, really good model that can produce much more accurate solutions. So we are big, big consumers of computer power. We probably, aside from like national security agencies, we have some of the biggest computers in the world, and we could use computers that are 100 times larger because it's a big, complex system. So this is what we do. We build these models. We build these for all sorts of things, from how hurricanes work to how the climate system works and everything in between. So this is what we do. And then we use these models to look at both past and future climate to better understand what have been the sources of change and what are our projected changes. So these are from simulations using models. We simulate climate from 1850 to the present. And this is temperature on the y-axis. So we have two sets. We run the model with two sets of conditions. And just like analogy, you chemists, if they discover something, they can repeat some sort of new chemical reaction in a test tube. They can do it 100, 1,000, 1,000,000 times in lots of laboratories, and they can verify and assess the result. We can't do that. We have one planet Earth. So we make these virtual Earths that we can do lots and lots of experiments on and change the conditions on and get simulations. So this black line here is when we simulate the temperature of the planet, when we give the model, tell the model how CO2 and methane have changed in the past century. This greenish line down here is if we say, oh no, that's fake, we didn't put any CO2 in, there were no increases in CO2. So the fact that the red line is from the model, the black line is the observed temperature. So the model is able to replicate pretty well past warming. It was a direct response to increased CO2 and methane in the atmosphere. If you don't tell the model about that, it simulates temperatures that have not warmed at all. So we can use models to look at the past and evaluate the sources and causes of past changes. So then we project the future. And we, as I said before, we make these different assumptions. So these different lines, as we said, are different estimates of future emissions. And these are something kind of weird. It's called Shared Socioeconomic Pathways, or SSP. Again, it's like sociologists, economists, all sorts of people coming together and making projections about what future economies will be like, what the politics will be like in the future, things like that. And they come up with these different estimates. And these are, in my mind, just orders of magnitude. What happens if you put a whole lot in? What happens if you take drastic action? What happens in between? And so we, in some sense, need as a planet to choose which of these lines we want to go on in the future, in the next 80 or 100 years. That matters a lot. So when we do this, we then project how temperatures and things like that have changed. Sorry, it's probably very hard to see, but this is a temperature from 1950 to 2100, so the year 2100. This is temperature on the y-axis. These different lines correspond to what happens to temperature if you follow those emissions pathways or those amounts of CO2. So a key point here is that even in the most aggressive reduction pathway, assuming that we're already reducing CO2 emissions, we still warm. The planet takes a long time to change. This is maybe a poor analogy, but I'll use it anyway. I'm sure you've all seen the movie Titanic, and there's that point in the movie where the guy is up in the lookout tower, the parapet, whatever it is, and all of a sudden he sees iceberg ahead, and he calls down, iceberg ahead, change your course. And immediately they flip the wheel as hard as they can, but the ship is still going by that iceberg. And he's calling down, why isn't it changing? Why isn't it changing? And eventually it slowly changes. Well, the climate system is a little bit like that, in that it takes a long time to make a change. And even though if you reduce emissions here, we're still going to warm for a while because there's a lot built in. So it's a very slow system. So already the next 20 years are kind of baked in because we can't change emissions that rapidly. So we're on a pretty well-known profile out to 2040 or so, something like that. It's that period after 2040 that we really have an opportunity to change and turn that wheel even harder for the climate system. And there are lots of important things going on here. This is global sea level change. I want to mention this because this is a really important thing, and it really impacts here in New Jersey with the coast. So sea level is rising. We already know that. It will continue to rise. I'm very, very confident in that. But there are two sources of sea level rise, and they really matter. One is the fact that as you warm the ocean, warmed water expands, And so as the planet warms, the oceans get taller because the water is warmer and it expands. And that's what's giving, so this is global mean sea level change. So this is 0.5 meters, 1 meter, 1.5 meters. So going forward, these different colored lines, and they all show increase in sea level, even when we're reducing CO2 now, of order 0.5 to 1 meter. So that's up to about 3 feet. And you can imagine, 3 foot sea level rise along the Jersey coast is a pretty big deal. Then when you pile the potential for more severe storms and hurricanes on top of that, that's very bad. But there's a huge uncertainty here. This is actually pretty well constrained. We know it will sea level rise with warming. But this dashed line shows the potential of what will happen if the ice sheets change. There's a tremendous amount of fresh water tied up in the Greenland and Antarctic ice sheets. And we don't really understand how they work, or we have good models of them. So that is a huge uncertainty in the climate system. That's a bad one. Because if there are instabilities in the ice sheets, you could have huge chunks dropping off that would have huge implications. So that's a big, big uncertainty in the climate system. So going forward, there are lots of things, extreme heat, heavy rainfall, I'll mention this in a minute, that's a big deal here too, because as the climate system warms, there's more evaporation, more water vapor, it has to come out somewhere. Yes, please.
Okay, you mentioned earlier in your presentation about I forget how many years ago, the change in the tilt of the Earth's axis.
Right.
Will the issues you just spoke of with sea level change and melting of the polar ice cap affect modeling the potential effect of changes in the axis, or not?
No, that's a really interesting question, and it wouldn't surprise me if there is some effect that may be small and slow, but it could have an effect. There are lots of interesting things going on here. So many interesting things here going, but it could on these time scales. So we're very short of time here, so I don't want to go over because I know you're on a schedule here. But all of these sorts of changes we're already seeing now in the climate system, whether it's extreme heat or ice sheets melting or storms. But in particular, here's an event we just saw last Friday. These are some clips from the huge storm that inundated New York City. This sort of extreme rainfall event is exactly what one of the things that models have been predicting for a long time. There's some crazy scenes of water flowing down the subways. I'm sure you've all seen these. But I'll take 10 seconds to make a plug here. This is a paper our group published earlier this year. It says, increases in extreme precipitation over the Northeast United States using a high-resolution climate model simulation. So these sorts of events are exactly what we're predicting in our climate simulations. So we say that by middle of the 20th century, the model projects unprecedented rainfall events over the region and even worse by the end of the century. So we're getting to the point where our models are good enough to make really specific projections about some of these things. Yes?
To your points about projections in the future and to the computer and high-resolution models that you're using, can you explain to us what does that mean when we have quantum computing available to us? And will that offer solutions, or will it offer ideas?
I don't know anything about quantum computing, but if it allows more calculations per second, then it will help. That's all I can say. I don't know anything more about that. Sorry. Okay. Yeah. Yes.
So the United States, UK, and other countries, they do a lot of work to reduce CO2.
Yeah.
But at the same time, other countries, they're going through the industrial revolution right now,
Yeah.
and they need it because they need to supply
Sure.
for their own people. It's very difficult, I bet, for you to try to put together some sort of scenario where you have so many other players in the war that are doing many things that are totally contrary to what we do here.
It is difficult, but I think the solution there, and again, this is a political solution outside of my area, is to, we think of countries in the tropics, for example. Boy, there's a whole lot of sunshine there. They're great candidates for cheap solar power all over the place. So I think in developing countries, they need energy. They want energy. It's for a better quality of life. It's for health. It's for safety. So they should get that energy. But it's how they make the energy. And so if you have lots of solar facilities in developing countries, that's a way around this problem. It's a win-win in my mind. So it's helping those countries who really need more power to improve their economies, to improve their safety and health of the citizens, to help them to create that power, but without releasing CO2 into the atmosphere. And it can be done, I think. So anyway, yes. I'm going to finish up because I know we're right on the deadline here. So we're
So alternative energy sources. So I'm thinking of the ocean wind farm.
Yep.
Can you give us the science on how that directly correlates, or if it does, to the marine life and them feeding themselves and whatnot?
Yeah, so I think that anytime they put in an offshore wind farm, there's certainly lots of studies about how that's going to affect marine life. And like anything, there's a trade-off. Is it harmful to the marine ecosystems? Maybe a little bit, but everything is risk. There's no perfect solution. So I think you have to weigh the risks versus the benefits, and I suspect they're okay in that regard. But yeah. So anyway, we are right on time here. So let me just finish up because I know you have a tight schedule here. So my take-home points. I hope they're your take-home points too. And these slides will be sent around to everyone if you want to peruse them, or you have trouble falling asleep, you can look at them. So Earth's climate is shaped by the energy balance. The energy is key, how the energy flows through the system. It comes from the sun, but how it's distributed then is really key. And the natural greenhouse effect is huge. Remember that. Without that natural greenhouse effect, we wouldn't be here. Modern climate now is shaped by changes to the greenhouse gases from human activity, possibly starting with early agriculture, which is a really interesting idea to me, but clearly accelerated by the Industrial Revolution. The future climate change, really the take-home message is there is some climate change baked in already to the system, but it's really up to the decisions we as humans make. How much we want more energy, but the question is how we create that energy. It's that simple. Do we create that extra energy by putting CO2 and methane in the atmosphere, or through alternate means? That's the question, and that's something that society can decide in one way or the other. There are clearly uncertainties in our understanding and ability to project the future. It's certainly not perfect. We're ever refining our models, hopefully improving them, making our projections more robust. There are legitimate uncertainties which we're working on, but those uncertainties are about how much warming is in the system, not whether it will warm. So it's a matter of, will it warm 2 degrees, 3 degrees, 4 degrees, legitimate uncertainty about that, but we know it's going to warm. There's just no doubt about that. Anyway, so thanks you so much for this invitation. I really enjoyed it. Thanks for all the great questions. It was really great.
Your Town Tube is today's #1 all-local promotion, social media, and networking in the Princeton-Mercer region. The most effective, attractive, quickest, and affordable ways to reach a huge local audience.